So, hi everybody. I hope you're kind of coping well with all the new situation that's been put upon us by this mysterious virus going around. I hope you find time to focus properly and to get your work and studies done. In a sense, you have a number of good resources available to you. The book, of course, is the thing that you can rely on, complemented by the notes that I put online, the exercises that are given to you, so hopefully you can still keep up the learning tempo as it is. I've announced on Canvas that the midterm exam has been cancelled for obvious reasons. That means that the final exam, scheduled at the end of Block 5, would count for your total grade. There will be more details about all of this when we next meet live, or when I actually add up some communications. But for now, we just carry on with the program as it is according to the plan of the course. So, what's the subject of the session that we want to treat, that we want to do this week? Well, it's magnetostatics in matter. During last week, we discussed the basics of magnetostatics, and this week is actually a relatively short lecture, I guess, where we complement that to include the presence of matter that has a certain response to magnetic fields. It's a bit parallel to what we did to electrostatics. So let's see how we want to get started. Well, there's a thing that we need from the end of the last chapter in order to really discuss magnetostatics and matter properly. And that's the multipole expansion of the vector potential. So I'll just write that down. Multipole expansion of the vector potential A. Okay, so we had a basic formula for A. Let me start with this. Basic formula for the vector potential A, given by a loop of current, also by a current loop. And that formula was in the notes. The potential, the vector potential measured at a position r that's generated by some loop of current is just mu0 over 4 pi, with the line integral now, so call it dl prime, of the current at that point, r prime, divided by r minus r prime. Okay, so that's the picture that you have. Imagine that you've got some loop like this, and you've got some current circulating in there. Now, the dl here is just the line element that parameterizes this actual thing. Here, I should write like a closed thing here. It's a closed loop. In general, you wouldn't necessarily need to have a closed loop here. You could just compute the contribution to the vector potential coming from a segment of a certain loop if you wanted to. But let's just do it like that. Okay, now as in electrostatics, we find that the expression that we have to integrate over has a kind of dependence in space, which is 1 over r minus r prime. Okay, so this spatial dependence this 1 over r minus r prime, you remember the magic of this. If you have a certain observation point r that is quite far away from the points you're considering here, then you can actually expand this fraction 1 over r minus r prime in useful fashion. Okay, and that's the kind of generic formula that we gave when we discussed the multipole expansion of the electrostatic potential. So this 1 over r minus r prime you can rewrite as a series. Sorry, interestingly, this magnification always happens at the wrong moment, doesn't it? So what's this series? It's just 1 over r over all power, and now a summation over integers from 0 to infinity of the magnitude of the vector r prime divided by the magnitude of the vector r to the power L with the Lth Legendre polynomial of the angle cos theta, or cos theta prime maybe, between r and r prime. Okay, so this is just a situation where you've chosen your coordinates so that the angle describes the opening between the r and the r prime. Okay, so this is just like to remind you of exactly what we did in electrostatics. Now, how do we want to use this further? Well, it's relatively straightforward because we can essentially just plug this expansion into the expression that we have here for a line current. Now, what we imagine, let's imagine that my loop here I view as the source, just to have the notation, what I mean. Same loop as before, almost. Now, I will use the subscript S to denote the sources. So what do I mean with this? I will write the expression for A of R and then just discuss it. A of R is mu 0 over, so let's imagine I've got current I here, so mu 0 I divided by 4 pi, that's a pi, summation from L is equal to 0 up to infinity of 1 over the vector r. So let's say I've got my vector r here, and let's say that that's my origin, and this is my vector rs, s for source. Okay, and then I've got a little element here which will be a little dl or dls. Okay, so 1 over r modulus to the power L plus 1. And now what I want to do is do the integral over the closed path represented by the loop here, so here, of the vector element along this path, which I'll denote as dls. So that's a little vector s for source. And now I have the power of the source vector to the power L like this, with now the Lth Legendre polynomial of the angle between the two vectors, which is really just the dot product of the two unit vectors, r and rs. Okay, so r hat is just the unit vector going in the direction of r. rs hat is just a unit vector going towards the source, and dl is just the little element that I integrate over on this list here. Okay, and then so I would have a certain line charge associated to this position here. Maybe I would write this line charge density as something like some lambda as a function of the position rs. Okay, that could be one way of writing all of this. Now, there are a few things to be said. So term by term, if we look at this, we get a similar expansion to what we had for the electrostatic potential, namely the first term. Well, let me just write the constants first, mu 0 I over 4 pi. And now we will just write the first few terms here. So the first one is just 1 over r, and I've got the integral over the path of the displacement along the path. Okay, so dl source like this. The second term, I've got 1 over r squared. Okay, r is just a modulus of r here, that I just simplified the notation a little bit here. And then the integral I need to do is again the integral over the closed path of DLS. And now I've got the RS cos theta, where let's say that so angle between R and RS. Yeah. So maybe I shouldn't even draw this. Yes, RS, so theta would be the angle between the two. Okay. And then I've got another term, which is a quadrupole term that I'm actually not going to write down for now. Okay, and it carries on to infinity like this, with this wonderful terminology that we had for the higher multipole moments. Now, important point, so nota bene, it would actually need to be emphasized even more than that. The monopole term that one, it always vanishes. So that means that the first term is the dipole term, and so let me just write it down. So it's the first non-vanishing term in general. Okay. Of course, you could have a zero dipole moment, but actually, quite generally, the dipole moment is the important one. Okay. What we can do is just rewrite it in a slightly cleaner notation corresponding to what we have here, or maybe I'm just jumping from notation to confuse you more or less deliberately. So let me just do that. Vector potential. The dipole contribution evaluated at a certain point r is equal to mu 0 I divided by 4 pi. There's a 1 over r squared, and now there's going to be from this loop an integral dl dls with the r hat dotted into rs. Okay, so that's the object that we need to calculate. Okay, maybe in the notations sometimes I'll switch to rs r prime. We'll see how we do. Okay, now there's a useful little identity that we can use to simplify this this expression here. So useful identity. And that's from problem, let's see, 1.61e in Griffiths. Not that Griffiths invented or discovered this identity. It's just in one of his problems. What's the idea? Is that if I consider a closed path integral of the following generic object, I have a vector c, which can be anything, dotted into r, and I integrate this whole thing over the path that I have here. The statement is that this is equal to the following object, vector A crossed into C, where A is by definition the surface integral of the area element of the path of the surface whose boundary is this path here. Okay, so P is the boundary of S. Okay, I don't know if you're familiar with this notation, just to kind of just to the boundary of the surface S is the path that I have here. Actually, so this is proven in the notes. Whoops, sorry. So the proof, I'm gonna leave this as an exercise, because once again, this is just a question of playing around with the notations a little bit until you you see what you get. I've copied essentially the solution of this problem in the notes at the end of chapter 5. Be careful, because I just updated that. There were a couple of typos in the previous version, so I've just re-uploaded the pages 512, 513 to correct those typos separately from chapter 6. Okay, so let's just get back to this thing. So in our problem, or in what we were doing above here, what we need is the following thing. So we need the this integral, right? So we need the integral of dl of the source that we have, of the vector r hat dotted into the source vector like this, rs. And now using this wonderful little identity here, where I can just substitute, you see here, I can just choose this C however I want. So I can just put this this thing to be corresponding to these vectors here in this identity, and what I get is that I can just like write this, just reordering this this thing with a minus sign. I've got the minus r hat cross literally what will become I mean this expression here, but I can just write it explicitly. So the integral over the surface of the differential surface element, okay, of the source, right? So it's really just, I mean, if you want it, it's kind of clear to visualize what that is. You have your path, and you take surface which is bounded by this path. Actually, it doesn't matter which surface you take. And then on these elements of the surface, you define a kind of normal vector coming out. And the surface integral that you have here is really, if you want, the surface average of this normal vector coming out. Yeah, so averaged with the surface area that you have. Okay, so what that means is that my dipole moment or my dipole part of the vector potential can be written in a simplified fashion. I can write this thing as mu0 over 4 pi. With now the following object, I will define a vector m, which will be the dipole moment, cross that into r hat divided by r squared, where m is the magnetic dipole moment, so magnetic dipole moment, and we'll underline that and give the formula. M is by definition I with the integral over the surface that's bounded by this loop of dA. Or if you want, it's just I times the object A here, where A is defined as this average here. writing some tautology here, right? Some very simple thing. A is by definition just the integral dA over your surface. Yeah. So so that's the idea, you know. So you have a certain loop carrying current. It represents a certain, or it encloses a certain surface. This surface has a kind of effective vector coming out of it, which is represented by the surface average of the normal vector that you have here. And the magnetic dipole moment is the product of these two things. So it's an oriented vector that is proportional to the current going through your loop, but also to the area of the loop. Okay, it's a bit as if it was related to the, you know, yeah, you think of flux going through and things because it's proportional to area. It's a useful way of thinking. Okay, so so that's just the definition. The important thing is that you remember that the magnetic dipole moment is really the leading contribution that you can get to the vector potential. Okay, so now here we are. So that's the one thing you have to carry through from chapter 5 into chapter 6. Okay, so so some, you know, some basic things of magnetic dipoles. Okay, so this is quite straightforward to go through. I'm sure you've kind of come across these things in your previous courses anyway. But let's just rehash a tiny bit, a couple of properties of these things. So, what's the kind of simplest picture that you can have for magnetic dipoles? Well, it's very simple. They're really just like little loops in which currents circulate. So you can think of dipoles as originating from lots and lots and lots of different things. Be that maybe a wire in a circuit, be that maybe an electron orbiting around a nucleus somewhere. It's just a very, very small orbit, but still you can picture it as a current rotating around a certain center. And this current rotating around a center represents, I mean, there's a certain amount of current, of course, but the area associated to it means that this object is inherently magnetic. It creates the field of a magnetic dipole. Not a perfect dipole. A perfect dipole is the limit of having infinite current, but very, you know, zero area, such that the product of the two remains finite. But in general, all matter, which is constituted of charged particles moving around, does have a magnetic component to it. It does create essentially a certain amount of magnetic dipole. So you take some different pieces of material, they'll have very, very different tendencies to create these dipoles, but nonetheless, everything that has charge and circulates will create that. Okay, so what are basic physical properties of these dipoles? Well, the first thing to say is that dipoles, I should always write like magnetic dipoles, so they feel a torque when put in a magnetic field B. Okay, so what's the picture? Let me maybe try to reproduce the kind of simple picture that you can have for this. So let's say you have a current loop of that shape. So I've got my current going this way. You know, current is conserved, so it just circulates around here. And let's imagine that I have a magnetic field which is going up like this. So that's my B. Okay, you see this surface here, let's imagine that it's a flat surface. So if I calculate this vector here, what I'm going to get is just a vector going perpendicular to the surface like this. Okay, so this would be like the vector A. Now, if I kind of displace it this way, maybe, hey, I'll do that trick that you can't do on paper just to have fun. So let me displace this B back here. Okay. Let's imagine that I define the angle between these as being some angle theta. Then there are a few things that that occur. You see, if I look at the current going through here, well, a few things happen. Yeah, so I've got currents here, currents here. The force that I get on these different sides of the loop are different, right? Because I don't know if you can picture, essentially every single current here is going to be like repelled from this magnetic field here. Just think of the V cross B thing. You remember V? So I've got charges moving this way here. V goes this way. B is like that. So that gives me a force this way for this loop here. Yeah. So this little loop has a force going that way. This little loop has a force going that way. Okay. So that's a little force, a little force. But you see, these things are pulled against each other. So there's no torque at all on these coming from the force on these two here. But here for these two, the V, the current goes this way, so it's as if you had charges moving this way. But then if I do V cross B, I have a force going like this, if you want, in the plane, and this one has a force going like this. And I don't know, if I do another drawing where now I'm looking at it this way. So here's my B, and now I'm looking at my problem along this way. Okay, I don't know if you can picture it. So these are, so I've got my current flowing this way. This edge here is this edge here. Okay, this one is hidden behind here somewhere. But now you see, and here I'm looking at this piece of wire on the end. Yeah, just at the axis. This wire is just like piercing the page. Now the forces that you have here are different, because now my force is going this way and my force is going this way. All right. So the torque that I get is proportional now to the sine of this angle here, right? So if I report the angle, it's just like here. So the force component is the sine of this angle. In total, you can just think about it a little bit. So the torque maybe I'll just give it a symbol. Okay, so the torque is just like the distance times the force as a vector, and here I would get that it would be let's go it like this. So yeah, I mean I should have defined all my areas and things. So I've got the area, the force, the sine theta, and now this is going in the direction of the x-axis, which is this one, right? So let me just put the x-axis here. This is the x-axis. Okay, so this would be like this. Okay. So that's for the particular case that we have here, but really we can just recognize that I mean the force has to do with the current that goes in here. So the little f that we have here, what is that? Well, there's the current, there's the size of the loop that I have here, right? So here I should put some dimensions onto onto this here. So let's imagine that the side here has a certain length a. This side here has a certain length b. Okay, so then this force here, this distance that I have here, is the b length that I'm sorry, I put it the other way around. I want my yeah, so forget about that. So I want to just put my length. Sorry, let's try to undo this. Yes. Well, let's do it the old-fashioned way, shouldn't we? Yeah, let me just cross that out. Okay, so let that length be b, and that length be a. So you want the total thing like this. And this force here, so now this length is b, so the force that I get for the torque is just I times b with this sine theta, but now the force is proportional to the magnetic field, so I've got this. Okay, so now we can recognize, because the product of A times B is really the area of this whole thing, which is really, again, the notation is a bit unfortunate, but the vector length here is the surface that I have here, which is little a times little b. Okay, but in better notation, my torque N is equal to the magnetic dipole moment cross the magnetic field B, where in this case M is just really this this quantity that I have here, right? So so the M that I have is I times A times B in the direction of this vector. Okay, so again, in an atrocious notation, I will have this, right? So in the vector a hat. So this is the vector a hat is the unit vector in that direction. Okay, but that's the important thing. So the torque on a magnetic dipole is simply the cross product between the magnetic dipole moment itself and the magnetic field. Okay, so so you expect, you know, some kind of complicated physics with this if you put some magnetic field, because things will tend to respond and reorient themselves with the field. Okay. There's a little, let's see. So as a little exercise for when you have time. Well, the first statement would be that the force on a dipole, when there's a uniform magnetic field, so the total on a total force on a dipole in a uniform B, that's going to be equal to 0. Why? Because essentially you could just calculate it. So the total force would be just the integral over your loop representing your dipole of dl, maybe carrying a certain current I, crossed into the magnetic field. But now, because the magnetic field is a constant, you can just take it out of the integral. So you've got the integral dl, but now you can draw parentheses around this, crossed into b, but because you've got a closed loop, this thing is equal to 0. So this whole thing is equal to 0. Okay, so if you put a uniform magnetic field and you throw dipoles in there, there will be no total force. There will be no drift force on the dipole. However, if you have a spatially inhomogeneous so if the field varies with position, then there will be a force on your dipole, which just corresponds to the gradient of the quantity of the magnetic dipole moment dotted into B. Okay, again, this is a little problem. So this is problem 6.4, which I will let you have a look at by yourselves. Okay. So let's see. Now, there's a little discussion in Griffiths about the effect of a magnetic field on atomic orbits. Yeah, by which is meant the electronic orbits around around atoms. So this is quite basic. I mean, the idea is that you just have, let's say you've got your atom here, and you've got your electrons flying around in circles, as you can see, around this. Now let's imagine that, so this is your z-axis, z hat is this way. There's a charge, your electron's here, it's got charge minus E, and let's imagine that it's moving at a certain velocity v in the counterclockwise direction of the circular motion. Right, so so you can do some calculations here. Maybe I mean I'm not sure it's worth doing this here. Let me just refer you to Griffiths for the actual numbers. So let's see, in my version of the book, this is section 6.1.3 for the discussion here. But I just want to say a couple of things on this. What's the idea? The idea is that the electron with its orbit represents a magnetic dipole, and this magnetic dipole will react structurally to the presence of an external field or not. Actually, the discussion in Griffiths is just a kind of classical model for this. Of course, when you start doing quantum approaches for this, the correct way to do it, you get ever so slightly different results, but still it's quite simple. So what's the idea? The idea is that if you were to put a magnetic field onto this setup here, let's say you start threading, let's say you put a magnetic field here, B, then what would occur is that your electron would have a tendency to speed up, because the additional presence of the magnetic field here introduces another force. You remember the force law, so V cross B. This V cross B is going to give you a force, which means that you're kind of contributing to the centripetal acceleration in this problem. So for B greater than 0, the electrons speed up. So what does that mean? The electronic dipole it changes. Okay, because the electrons speed up, if you want, there's an additional current that goes in there. And this this extra dipole moment it goes against B. Okay, and the fact that you react by trying to compensate the external field, thereby reducing it a little bit, this is called diamagnetism. Okay, so if you were to do that with a real piece of matter where this model is kind of applicable, what you would see is that you would apply your magnetic field, but then you would notice that if you were to measure the field, like in the presence of this, it would be slightly reduced because the external field creates a dipole moment here that goes against the applied field. And the size of this dipole moment, I'll let you look at Griffiths for this. Anyway, this is like an incorrect model for this. It's meant just as a simple illustration of what it can be. Okay, so let's just move forward a little bit with our discussion in matter. Maybe what I'll do is that I'll pause this video for now and then carry on with just the actual continuation into matter. Okay, so